A warm welcome to all the viewers for the course Advanced Manufacturing Technology. Myself Thiapal, Assistant Professor of Department of Mechanical Engineering. Today I am going to give a lecture on laser beam machining. Obviously this will be the part 2 lecture for laser beam machining. Already in the part 1 we have discussed the basic working principle of laser beam machining. But today in this particular lecture we are going to discuss about the mechanism behind the laser beam machining. But along with that we are going to calculate how the MRR is calculated, how the depth of cut has been considered, on what are the lasers which are used for what type of applications we are going to discuss in this particular lecture. So before we proceed with the lecture, it is very essential for us to go with the content. So let's have a look at the content. So as you can see in this content, first laser, obviously we will be giving a brief introduction about the laser. Then we'll be going with the laser beam machining. What are the types of laser that are there? Laser applications. Along with that, we are going to talk about the parameters affecting laser beam machining. This is the main portion where we are going to focus today. Next, little bit advantages and disadvantages we'll be discussing. So without any further delay, now let's move to the next slide. So from this pictorial view, you are able to see a laser beam machining. Basically, this setup was made by Asia, and you can see how this laser light, it is being focused over the workpiece. And you can see the spark has been generated, and here the material get vaporized and the material removal occurs. Okay, so now let's move to the next slide. So here what we were talking about laser, isn't it? Because our entire topic is related to the laser beam machining. So what we know is that laser beam machining, or more broadly laser material processing, basically deals with the machining and material removal processing like heat treatment, alloying, cladding, sheet metal bending, etc. Now, such processing is carried out utilizing the energy of the coherent photons of laser beam, which is mostly converted into thermal energy upon interaction with most of the material. Nowadays, laser is also finding lots of applications in regenerative machining, or in fact, we are talking about rapid prototyping, as in this process like stereolithography, selective laser sintering. So these are all rapid prototyping machining where we are effectively using laser for performing the machining. Now, if I go for a look, I have already told you that laser basically stand for light amplification by stimulated emission of radiation. And the underlying working principle of laser was first put forward by Albert Einstein in the year 1917. And if I think about the industrial laser for experimental development, then it was done in the year near about 1960. So already we have discussed about this portion in my part 1 lecture for laser beam machining. Well, we will be just discussing about this laser in some different way. That is, laser beam can be very easily, it can be very easily focused using the optical lens, isn't it? As their wavelength range varies from half micron to 70 microns. And the most important thing is that focused laser beam, as indicated earlier, can have power density in excess of 1 megawatt per millimeter square. Next, laser interact with the material. The energy of the photon is absorbed by the work material, leading to the rapid substantial raise in local temperature. And this in turn results in melting and vaporization of work material. And finally, the material is removed. And here what I have told you is that basic thing. That is laser beam machining. When we are talking about, it is none other than thermal processes. And this is told that this is the mechanism for material removal. As I've already told just now that laser interact with the material, isn't it? Otherwise, how the material will be removed? So first thing is that laser basically interact with the material and the energy of the photon is absorbed by the work material, and this lead to the raise in local temperature to rapid substantial and thus result in melting and vaporization of the work material, and finally the material is removed. So ultimately what I have already told you, that is always in laser beam machining the material is removed in the form of vaporization and melting. This is one of the most interesting point for this laser beam machining. And the most important thing is that there are several non-traditional machining processes are there, but still the advanced machining process, one of the advanced machining process is laser beam machining. Not only laser beam machining, but also electron beam machining is also one of the advanced process. Okay, and laser beam machining is the best suited for brittle material. Is it clear to you? Brittle material cannot be done machining in a proper manner with the conventional machining process. Means you can go with that, but if you want to get a good thing or good accuracy in the product, then you can go with brittle material also. The most interesting thing is that, and that's too with low conductivity. But it can be used on most of the material also. Don't think that only brittle material is applicable. No, you can go with some other material also. Now, if you think about the rubber material, just have a look here. If you think about the rubber material, you can see the diameter that has been generated, it is of 3.4 millimeter. And you can see the thickness of the plate is 3.1 millimeter. And if you go with the plastic material, you can see the depth is 1 millimeter. So this is the thing, and if you have a look of this particular figure, then you can see in a very simple manner that is power supply is there. There is a flash lamp, there is a reflecting end, there is a laser crystal, and partially reflected end you can see with the help of this lens. I told you that you're going to focus the laser beam with the help of lens. And you see over this workpiece, it has been ejected. And what happens? The material gets melted, it gets vaporized, and the material is removed. So at the beginning, I told what is laser. Whenever you go for the laser beam machining, the first thing arises in everyone's mind. What is the full form of this laser? It is an acronym for light amplified stimulated emission of radiation. Next, laser is also a device which generates or amplifies light. Stimulated emission or electromagnetic radiation, these are the thing that is related to your laser beam machining. And last, not the least, that is it is coherent, monochromatic, directional and high power laser basically used for machining purpose. So you can understand that what are the factors that you should keep in your mind while selecting the laser. It is coherent, it is monochromatic, it is a directional and high power laser beam. So what I have told that before we go with the material removal rate and all those things, little bit we should be aware of the process also. So now let's have a look for the process in a brief manner. Now at the zero level condition, we are considering the working principle from the zero level. The atom is considered at the ground. Okay, so at the initial of the process, if I consider from the zero level, then the first and foremost thing is that atom is at the ground level. This is because always the electron occupy the lower potential energy. So we can't do anything else because electron always occupy the lower potential energy, And that's why the atom is considered at the ground level. Now from the external sources, what we have to do is that this ground level electron absorbs some energy to stimulate high stage. And these electrons are moving from the lower to higher level energy. And when this electron reach the higher energy level, at that particular instant, we observe the unstable band of energy. And by releasing the photons, within a short time, it reaches the ground level. And such process is known as spontaneous emission. So coherent laser beam is created in this way. Again, I am repeating how coherent laser beam is created. So if I consider the process from zero level condition, then the first thing we obtain is that the atom is considered at the ground level. This is because the electron occupy the lower potential energy. And from the external sources, the ground level energy absorbs some of the stimulated energy to get into a high stage. And these electrons are moving from one lower stage to a higher energy level. And the most interesting thing is that when the electron reaches the higher energy level, at that particular instant, the unstable band of energy is observed. Next, what they do is that they start releasing the photon within the short time. It reaches the ground level, and such process is known as spontaneous emission. Such process is known as spontaneous emission. And this way the coherent laser beam is always created. So you can see this is your stimulated emission. This is your before emission. This is during emission, and this is after emission. Okay. From here in this figure, you are able to look the thing. So if I consider the laser beam machining process from this particular figure, then in this model of atom, negative charge electron rotates around the positive charge nuclei in some specific orbit. Okay. And the geometry and the radial of such orbit part depends on a variety of parameters like number of electron, presence of neighbor atom, and their electron structure that is present in the magnetic field. Each of the orbital electron is associated with the unique energy level. At absolute zero temperature, an atom is considered to be a ground level, when all the electron occupies their respective lowest potential energy, and the electron at ground state can be excited to go for a higher state of energy. And by absorbing the energy from the external sources like increase in electronic vibration at elevated temperature through chemical reaction as well as via absorbing energy of the photon. Now what happens on reaching the higher energy level? The electron reaches an unstable energy band and it becomes to its ground state within a very small time by releasing a photon. And this is called your spontaneous emission. Now if you look at this particular figure, the spontaneous emitted photon would have the same frequency as that of the exciting photon. Now sometimes such changes of energy state puts the electrons in a metastable energy band. Instead of coming back to its ground state immediately, it stays at the elevated energy state for micro to millisecond. And in the material, if more numbers of electrons can be somehow pumped to the higher metal stable energy as compared to the number of atoms at ground state, then it is known as population inversion. Okay. And such type of high energy metastable state can return to the ground state in the form of any avalanche provided stimulated by a photon of suitable frequency or energy. And this is known as stimulated emission. And most important thing is that it is stimulated by the photon of suitable energy. Then the electron will come down to the lower energy state, and in turn one original photon, another emitted photon, by stimulating having some temporal and spatial phase would be available. And in this way coherent laser can be produced. There is a gas in the cylindrical gas vessel, if you consider, and the gas is called the lasing medium. Then one end of the gas is blocked with 100% reflective mirror and the other end is having a partially reflective mirror. Now population inversion can be carried out by exciting the gas atom or molecule by pumping it with the flash lamp. Then stimulated emission would initiate a lasing action. And this simulated emission of photon could be in all direction. Most of the stimulated photon not along the longitudinal direction would be lost and generate heat. The photon in the longitudinal direction would form coherent high directional intense laser beam also. So you can see how interesting the concept of this laser beam machining basically exists. So this is the photo that we were discussing about right now. Okay, so if I tell you that what is the thing exactly happening, then you can see here that is the change of energy state that puts the electrons in metastable state, or you can say the change in state of energy puts the electron in a metastable energy band. And the most interesting thing is that instead of coming back to its ground immediately, it stays at the elevated energy state for micro to millisecond. And sometime in a material, if more numbers of electrons can be somehow pumped to higher metastable energy state as compared to the number of atom at ground state, then it is called the population inversion. And here you can see this is the energy level, this is the energy, this is the highest, this is the lowest. You can see absorption is occurring here, spontaneous emission is also occurring, and this is the energy band in a material. So laser beam, we have discussed so many things, isn't it? So laser beam basically it is using always a highly coherent light source. And most important thing is that this beam can be focused by means of a lens on a very small spot in a workpiece also. It doesn't mean that always a big machining is required or big hole drilling if you require that we will be going with the laser. But if you want to eject a small spot in the workpiece, then also it can be done with your laser beam. And basically the equipment consists of nothing. It is very simple structure. It consists of a ruby crystal which is placed inside the flash lamp, and basically the flash lamp is used to produce high intensity of light rays. So you can see this is a very good picture you can see here. This is the laser beam. This is the laser beam you can see, and this is the gas nozzle, and through this electrode this can see pulsed arc has been generated, pulsed arc you can see, and you can see the fusion zone. This is the fusion zone. Okay, so interesting thing is occurring here, the fusion zone. So what this actually it is stating you, let's have a look here. That is, the ruby crystal is thus stimulated and this produced a high spatial laser beam. You can see from this particular image. And when the rays hit the work surface, it causes a partial or complete vaporization of surface material. So ultimately what we are talking about? We are just discussing about the vaporization. Always the vaporization and melting, the term is coming while we are going with the laser beam machining. So this is a very simple schematic diagram for laser beam machining. You can see this is an elliptical reflectivity cavity, There you can get the lasing material. Here you can see the flashlight. There is a partial mirror is there for reflecting the beam, laser beam. You can see a lens has been given so that you can focus the laser beam in a particular point of the workpiece. And next is focal length has been given to you. You can see. Now this entire thing you can control by a CNC control. There is a position table for the movement of the workpiece. Okay, and the total reflection of the mirror, you can see this is the upper portion. So how you can see that this is the total reflection mirror is there. There is a reflectivity cavity. This is the cavity. This is the flashlight you can see. This is the lasing material. Partial mirror is this one, and there is a lens for focusing your laser beam in this particular workpiece, and in this particular section you can see the material is getting removed by melting and vaporization. By melting and vaporization. So how the effect of beams basically affects the material. So this is the laser beam, you can see. You can see this is the laser beam. So it is getting thermal conductivity. Okay. Next, this is the laser beam when it is striking the material. This is the portion initially liquid is occurring, and if I go to the great depth, then you will see solid and liquid interface. Is that clear? This is the liquid zone of the material, and this is the solid and liquid interface. Now we will be seeing the basic material removal. How the material is removed. You can see this is the material removal is occurring. This is your workpiece. This is your workpiece, and this is the laser beam. It is getting strike. Just you see it is getting strike. And this droplet, you can see this droplet. Basically these are nothing. The material is getting melted. This is getting vaporized. You see this is the getting vaporized. And thus you can see you are digging or making a hole over the workpiece. A very simple thing. It has been explained here. There is nothing to get into details because already I have told what type of laser, basically the laser light is, then how the emission is occurring, what is population inversion is occurring. So everything it has been described early. And from this particular figure you are able to see just simply how the material is getting removed. Now, as I have already told, our next target is what are the characteristics they are basically associated. So first, material removal technique. What is the material removal technique? It's nothing. Heating, melting, vaporization. Because these are the three techniques that you are implementing for laser beam machining. Because laser light is initially heating the workpiece. If it is getting heated too much, then it is getting melted. And again, if you are continuously heating it, lots of amount of heat has been provided of the workpiece, then what is happening? Vaporization is occurring. So you can say one and another is interrelated to each other. Now this work material, basically the second parameter that or the characteristic is it's all about the work material. What type of material are you going to prefer? All material you can go except those who are having a high thermal conductivity and high reflectivity. So laser beam machining, not only it is able to machine every material, but still it has got some limitation for some material. Those materials are having high thermal conductivity and high reflectivity. So this type of material is avoided. Next we are talking about the tool. What is your basic tool for the material removal? Only the laser beam, because laser beam machining means only laser is required. None other thing is required. So what is the basic thing you have to keep in consideration? About the laser beam wavelength. And that wavelength should vary between 0.3 to 0.6 micron meter. Okay, you have to remember this is very important point. Okay, this is very important point that you have to remember. Next, we will be having look for power density. What should be the power? How much maximum power can be implemented? It's maximum 107 watt per millimeter square. Next, if I ask you what is the output energy of your laser, it is 20 joule. This is also one of the important point. Next, pulse duration. Already we have discussed what is pulse duration while we are talking about the machining for EDM. So pulse duration, it has to be between 1 millisecond. And last but not the least, we are talking about the material removal because it's all about this material removal we are performing the machining. So it is very essential that where in which non-traditional machining process material removal rate is high. So what important thing is that material removal rate varies between 6 millimeter cube per minute. Now dimensional accuracy. Whenever you are manufacturing a product, accuracy level it should be maintained. And you can obtain the dimensional accuracy between plus minus 0.025 millimeter. So the accuracy is also too high. Next, medium, where you can occur this one? Normally in the atmosphere. Okay, and what is the specific power consumption? It is 1000 watt per millimeter cube per minute. So you can understand what is the specific power consumption. 1000 watt per millimeter cube per minute. And efficiency is obviously less. Okay, that is between 10 to 15%. The efficiency is not too high. But still we prefer this particular process because some machining which cannot be done through any other processes, we basically prefer for going with laser beam machining. Though the cost is too high, because itself the laser cost is so high that itself its experimental setup cost is also getting high. I mean to say laser setup cost is also high. And next is the maintenance cost is also associated with this particular product. So this particular lecture, as we were talking, that what is the importance of this particular content for today's lecture? It is none other than the process parameter. Why we are using this particular process? What are the process parameter that you should consider while performing the operation so that you can control the machining in yourself? Okay. So first about the working principle, if I go, I have already explained to you. Now we are discussing about the process parameter. So third thing is that first is workpiece property. You should be aware of the workpiece property. Otherwise it will be difficult for you to know that whether the laser beam will be effective for this type of material for performing operation or not. So selection of workpiece material is up to you. So you can choose that process parameter. This is one of the factor. How much laser intensity would you like to prefer? So you have to keep in mind laser intensity also. Next, which gas you would like to assist? Helium, nitrogen, argon. Which gas do you like to go with? Next important is your focusing length. So focusing length, you're going to maintain the focal length, and in that way you are going to perform your accuracy for drilling some hole or performing any operation. And that is also depending upon you. What should be the focus length or focusing lengths that you would like to go for. And last but not the least, it is the interaction time. Time is one of the most important factor. Now just have a look. This is the interaction time. Okay. And this is the power density. And you can see here are so many things cube has been shown to you. So you can see if I go with ultra short machining, then you can see power density is high, but interaction time should be minimum. If I go for macro machining, or you can say if you go with the micro machining, then power density should be mediocre and your interaction time also be mediocre. But if you go for drilling cutting, okay, Your power density should be minimum, but time has to be, interaction time has to be maximum. For welding, you have to increase the time and your power density little bit less you have to implement than you are preferring for drilling and cutting. And cladding, here you have to do is that your time interaction is getting increased, but your power density is getting decreased. So you can see from this particular slot that how this power density, how this interaction time is affecting your every operation. It can be ultra short machining, it can be micro machining, it can be drilling, cutting, welding, cladding, any operation you perform. But you are going to vary the power density along with the interaction time. Now for every material there is a threshold intensity, and that has to be achieved for evaporation, okay, to occur. And laser beam machining process are located slightly above the melting line that enables melting and then vaporization. So whenever you are talking about the melting and vaporization, then you have to slightly increase your located temperature from the melting line. So you can see this is the melting line. This particular line you can see now, this is the particularly melting line. Okay. Now, the thing that we would like to discuss, it's all about material removal rate. The thing is that the intensity of laser beam does not vary with time. And laser beam is uniform over the entire area of the hotspot. So the material being removed is both being melted and evaporated. And the steady state ablation is characterized by constant rate of material removal and the establishment of a steady state distribution. So this is a basic form of your material removal rate. How you are going to calculate the material removal rate? Please have a look for the steady temperature distribution. That is T minus T0 by Tm minus T0, that is equal to E to the power minus Vx by alpha. And what is this Xc? That is alpha by V. So what is this V? That is steady ablation velocity. This V is steady ablation velocity. Okay. And you can see this alpha, what we are talking about, it is the thermal diffusivity of the work. What is the T? T is the temperature at a distance x below the ablation surface. And T0, it is the initial uniform temperature of the workpiece. And what is this one? Im that you have got, sorry, Tm. As I have already told, Tm is nothing but is the melting point of the workpiece. And what is this V? This V is your steady ablation velocity. And this alpha can be denoted by K by rho into Cp. So K, you know, K is what? Thermal conductivity. Rho is your density and Cp is your specific heat of the workpiece. So this is a very important formula that you have to remember. That is this one. It is very important. Okay. Now we are talking about the material removal. So after steady ablation is released, the relationship between the intensity, exposure time, thickness of material which has been removed and thermal property of the material, it can be defined by Ft, that is equal to K into Tm minus T0 into rho into H by F plus rho Hd, where T is your exposure time. This T, you can see, this is your exposure time. Now laser, we have discussed so many things about laser, isn't it? Basically, if I want to say what is the type of laser, then I must say gas laser, solid state laser and excimer laser. What is gas laser? An electric current is liberated from gas to generate a consistent light. And the most commonly gas that is used, HE, I mean to say helium, argon, carbon dioxide. And fundamentally, these gas act as a pumping medium to ensure that necessary population inversion is attended. So that population inversion, I have told you in the beginning. So the thing, we need a gas to pump the medium. Okay. Next, we are talking about solid state laser. They are designed by doping rare element to various host material. Unlike gas laser, solid state laser, or pumped optical flash lamp or arc lamp. Ruby is one of the most frequently host material in this type of laser. A ruby is a type of solid state laser whose laser medium is synthetic ruby crystal. Now this ruby laser generates deep red light pulse of millisecond pulse length and wavelength about 694.3 nm. And synthetic ruby rod is optically pumped by using the xenon flash tube before it is used as an active laser medium. What is your excimer laser? The state is different than in solid or gas laser. This is particularly a device which is a combination of reactive and inert gas to produce a beam. And the most important thing is that this machine is sometimes known as ultraviolet chemical laser. So this is helium and helium laser. You can see this is a cylinder. Helium and neon gas they are using as reverser. Laser board tube is there. This is the anode. This is the cathode. This is the output coupler. High reflector. Gas envelope is there. This is the laser output. So you are getting the laser output here. This is a ruby laser. Already I have explained you in my first lecture of laser beam machining. You can see this is the flash tube. This is the partial mirrored surface, this portion. These are purple color atom and this is also white color mirror surface. Excited atom, you can see this way they are getting excited. Emitted light, you can see these are the emitted light. Okay, these are the emitted light. And then what it is happening, it's getting here and it is ejected in this form of light. So this is particularly ruby laser. So excimer laser, you can see this is a combination of inert gas and reactive gas. So this is the gas supply and vacuum chamber is here. This is the laser cabinet. This is the computer control device and high voltage supply has been provided. Excimer is also known as ultraviolet chemical laser also. Now you can see the general application of laser in manufacturing. So if you go for cutting metal, like what type of laser you are going to prefer? If your cutting is the operation on metal, if you are using, what type of laser you are going to use? There is PCO2, CWCO2, ND ruby you are going to use. If you go for plastic, then you have to use only CeCO2 laser. If you go with ceramic, you have to go for PCO2 laser. For drilling, if you go for metal, you can go with PCO2, ND and ND glass and ruby. If you go for plastic, excimer you have to use. If you go for marking, then metal, then PCO2, ND plastic, excimer, ceramic also excimer. If you go for surface treatment metal, then you are going to use CWCO2. And for welding of metal, if you go, then you have to use PCO2, CWCO2, ND ND glass and ruby. Okay. What is this P? P is none other than pulsed. What is CW? That is continuous wave. And ND you know, neodymium, yttrium, aluminum, garnet. How you are going to calculate the depth of cut? Okay, so the cutting depth of laser is directly proportional to the quotation that is obtained, and it is divided by the power of the laser beam by the product of the cutting velocity and the diameter of the laser beam. So cutting velocity and diameter VD. P is, you can see, that is the product of the cutting velocity, or you can say this is the laser beam power. T is depth of cut, V is the cutting velocity, D is the laser beam spot diameter. And the depth of cut is also influenced by the workpiece material. The material's reflectivity, density, specific heat, and melting point temperature all contributes the laser ability to cut the workpiece. So you cannot just consider one factor, you have to consider everything. That is material reflectivity, density, specific heat, and melting point that is required, that melting point temperature is required to carry out the cut for the workpiece. Application already I have explained in the previous lecture also, but still few points I would like to highlight. These are some application that I have not mentioned in that one. This welding, cladding, marking, surface treatment, drilling, cutting, these are the common operation that is performed through laser beam machining. Okay. In automobile industry, shipbuilding, aerospace, steel, electronics, medical industry, all they are using laser. Laser is considered to be one of the advantages that can weld at a speed of 100 mm per second, as well as it has the ability to weld dissimilar metal also. So this is one of the interesting point for this particular laser beam machining. Laser cladding is used to coat cheap or weak part with a hard material in order to improve the surface quality. And drilling and cutting with laser advantages in that there is a little no wear cutting tool is required. I mean to say there is no wear in the cutting tool, as there is no contact to cause any damage also. So what are the advantages? Laser machining, there is no physical tool is required, no machining wear is occurring, larger aspect is there, micro holes can be drilled. Laser is processing is a thermal processing, but heat affected zone in the pulse laser processing is not very significant due to short pulse duration. These advantages already I have explained in the previous slide. I am not going to elaborate again. Its initial cost is high, maintenance cost is high if it not very effective process. Presence of heat affected zone if you're going with the CO2 laser cutting. Okay, and thermal process but not suitable for it, means that particular material which are having very high heat sensitivity, like aluminum, glass, fiber, laminate. So now you can see what are the application and which type of laser you are going to prefer. If you want to dig a hole for large hole up to 1.5 mm dia, then you have to use the Rabi laser or ND glass or ND YAG. For large hole, that is tree pan, then you have to go with ND YAG and CO2. If you want to make a hole, small hole less than 0.25 mm dia, then you go for the Rabi ND glass and ND YAG. And drilling, punching or percussion, then you go with the ND YAG and Rabi. Okay. If thick cutting is required, then CO2 with the gas instant. If thin slitting of metal is required, then ND YAG. If thin slitting of plastic is required, then CO2. If you go with the plastic material, then go for CO2. If you want to go for metal, then you go for ND YAG, Rabi and ND glass. If you go for organic and non-metal, then go for pulse CO2. If you want to go with ceramic, then you go for pulse CO2, ND YAG. So here this is very important because the application and the type of laser that you are preferring. So in this particular site you can see Rabi, ND YAG, ND glass, CO2. These are the various types of laser. Okay. Now what are this type? Rabi is a solid state, ND also solid state, ND glass is also solid state, only CO2 is only gas. What is the composition for Rabi? 0.03 to 0.07% ND in Al2O3, and for ND YAG 1% ND dop yttrium aluminum garnet. For ND glass 2 to 6% ND in glass, and for CO2 helium and nitrogen, that is 3:8:4. Wavelength has been also told 0.69 micron. This is 1.064 micron meter, this is 1.064 micron meter, this is 10.6 micron meter. Efficiency 1% maximum, this is 2%, this is 2%. For CO2 efficiency you are getting little bit more, that is 10 to 15%. For beam mode, this is pulse or CW, this is pulse or CW, continuous wave that has been, and this is the pulse and this is the pulse or CW. Okay. Spot size 0.015 millimeter, 0.015 millimeter, this is 0.025 millimeter, this is 0.075 millimeter. Pulse repetition rate, okay, 1 to 10 pps, this is 1 to 300 pps, this is 1 to 3 pps, and this is CW. Beam output 10 to 100 watt, 10 to 1000 watt, 10 to 100 watt, 0.1 to 10 kilowatt. And peak power 200 kilowatt, 400 kilowatt, 200 kilowatt, 100 kilowatt. So here we have come to a conclusion for laser beam measuring, and this particular lecture we have already discussed about the material removal rate, what are the depth of cut, how you are calculated. So the next we will be having a look for the quiz contest. Okay, so first question that has been asked to you, that is what? First question it has been asked to you, mechanism of material removal in laser beam machining is due to mechanical erosion due to impact of high of energy photons, electron chemical etching, melting and vaporization due to thermal effect of impingement of high energy laser beam, or fatigue failure. The correct answer is option C. That is, mechanism of material removal in laser beam machining is due to melting and vaporization due to thermal effect of impingement of high energy laser beam. The laser beam is produced due to what? Spontaneous emission. Stimulated emission followed by spontaneous emission. Spontaneous emission followed by spontaneous absorption, or spontaneous absorption lead to population inversion and followed by the stimulated emission. The correct answer is option D. That is, laser beam is produced due to spontaneous absorption leading to population inversion and followed by stimulated emission. So thank you for listening the video, and we have already gone through the working principle as well as what are the material removal rate, what are the process parameters that is affecting your material removal rate. All has been discussed in this particular lecture. So if you have liked the video, then please like it and subscribe the channel, and please stay connected with me so that we can discuss some other machining process, that is non-conventional machining process, in this particular course. Thank you. Thank you very much.